Hello, this is Dr. Michael Hassan, the engineering doctor, and this is lecture number 18, Design with RAM of the course Digital Logic Design of Chapter 4, Design with Standard Modules. Design with RAM stands for Read-Only Memory, is a very nice lecture intended to show you how to use the RAM to implement switching functions with a large number of switching variables. The next slide is a disclaimer for you to read. There are many references in digital logic design. I follow reference number 1. In chapter 4, the contents are decoders, decoder expansion, design with decoders, code converters, encoders, multiplexers, multiplexer expansion, and design with multiplexers and demultiplexers. We covered all these topics in the previous lectures, so please refer to them. Today we'll talk about read-only memories, RAMs, and design with RAMs. What's a RAM? A RAM stands for read-only memory, is integrated circuit modules that include a decoder to generate all possible minterms and a programmable OR matrix to implement any desired combinational function or switching function or network. So here we have a decoder. The decoder will generate minterms, and we know that any switching function can be represented as a sum of minterms. This is the canonical standard form. We covered this previously. Now, when we program the OR array, the OR matrix, this will allow us to pick up the minterms needed to represent each switching function. Now, the size of the RAM, of the read-only memory, is very important to satisfy the functions that needs to be implemented. So we look how many functions we need. We need, for instance, up to 8 functions, and each function may have 11 variables or 11 switching variables. Then we would need actually the next chip that I'm going to talk about. It will be very adequate for us. This chip is called 2716. It is 2K by 8 EEPROM. And this is electrically programmable RAM. It means can be programmed in the lab, not in the factory, by using a device called the Burnoff. So basically, we will burn the data which represent the OR matrix into the OR matrix by blowing the fuses that we don't need and keeping the fuses, the switches that we need. This will allow us to make the proper connections to choose the minterms for each specific function. The 2716 represents a relatively small size EEPROM. It has 11 input address lines and 8 output data lines. With this EEPROM, we can implement 11 switching variable functions, where each switching function may have up to 2048 minterms. Much larger read-only memory modules are commercially available. So clearly, we can implement a very complicated functions, huge functions, without any minimization required. Just we implement them by a simple program that we can write in ASCII code, can download it to the chip. Okay. As an example, we will try to implement switching functions for the Hamming code generator. The Hamming code generator, we have seen it before. It's a representation of the decimal digit from 0 to 9. So we are using only 10 minterms from 000 to 1001 for the BCD. And the Hamming code output, if you remember, we have the parity bit, 3 of them, P1, P2, and P3, and the digits, which is D1, D2, D3, and D4. And this is the Hamming code representation. So once we have this, we can represent P1, P2, D1, P3, D2, D3, D4 as a sum of minterms. To implement a set of switching function with a RAM module, we need to store the output part of the truth table of that set of switching function. The truth table can be expressed as a hexadecimal file and stored into the RAM by the programmer. Now, the programming device is called a burner. It's really not that expensive device, and it could be used to burn a variety of modules like ROMs, BALs, MPLAs, and GAL chips. So it's extremely useful. Now, consider the truth table of the BCD to Hamming code generator shown in the figure here. In this table, we have 7 switching functions to be implemented, and there are 4 input variables. Therefore, we need 24 by 8 RAM. We need 2 to the power 4 by 8 RAM, 2 to the power 4 by 8 RAM, which will do the job. So because we have 4 inputs with only data output assigned and assigned. So the other output, since it is not needed, the Hamming code, so since we have only really 4 input variables, so 2 to the power 4 by 8, because we may not really find by 7. By 7 is not a typical number to find a chip with this number, so it is 2 to the power 4 by 8. So we will have a 16 minterm by 8 output. Okay, so 8-bit word. And we will add the unassigned bit to the most significant position of each row. Therefore, the hex file, so how we represent the hex file for this data here? If you look here, the first byte, because we will add 0 to the most significant bit, will be 0, 0, 0, 0, 0, 0, 0, 0, or in hex will be 0, 0. The next one will be 0, 0, 0, 0, 0, 1, 1, 1. Again, I'm adding 0. It is not given here. I added just out of my head. So this will be 0, 7, and this is what we see, 0, 7. And you continue, you get 0, 0, 1, so it is 1 hex. Then you get 1, 0, 0, 1, and this would be 9, so it is 1, 9, and so on and so forth. After we finish 10, we have to continue to minterm 15, so minterm 10, minterm, and so on by adding zeros. So the last byte that you can see here, which is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 6 byte, because we have to put this data, otherwise you will get an error because the data have to be burned completely into the chip. It means those are really not used, and we will have zeros. So when we load this text file, like an ASCII simple text file, into the burner will program the EEPROM for you, programming process, break the fuse when the bit is 0, and exclude the corresponding minterm from the Boolean function. So if it is 0, we'll break the fuse. There's no connection. If so, the minterm will not be used or will be excluded. Okay? Now, how this will look, the fuse map, how it would look like, those are the D4, D3, D2 as sum of minterms. This came really the outputs from the truth table because we need them to look at the map. We need only, for the programmer, we need only this hex code, only this 00C07191E2B2C3235 4A4B0000. This is the only thing. This is a text file, and you upload it to the burner. Then you click on burn, and boom, it will be done. It's a very easy process. So those the sum of minterms came from here. As you can see, D4 is the sum of minterm 8 and 9. So it is 8 and 9, 8 and 9. See, 8 and 9. So this came from the truth table. D3 is the sum of minterm 4, 5, 6, and 7. And this is what we see it. 4, 5, 6, and 7, and so on and so forth. Okay? So once we have this, once we burn the chip, this is what the programmer will do. If it is 0, the minterm is not going to be selected. So we have from the output from minterm 0 to minterm 15. The input is D1, D2, D3, and D4. And so here is not going to be selected at all. Okay. D7, we are not using this because we don't need it. We are using P1, P2, and the last line is not used because we have 8 output. So for instance, D4, we are choosing only M4 and M5. So those switches will stay intact. They will stay closed. It means there's connection with the minterm. And all the other switches will be blown. It means there is no counter. The same thing, for instance, for D3. D3 will be M4, M5, M6, and M7. You see those fuses are intact here. Okay? And so on and so forth. So this will be the connection for the EEPROM after you program it, after you burn it. So once you burn it, you apply, you take the EEPROM, you apply the data, you put the power supply, the chip enable in and out has to be grounded. 2 supplies has to be connected to the chip. And after that, so you apply the inputs, any data you have, and you take the output to maybe to LEDs to see the, because this is a Hamming code generator, to see the Hamming code, which is for each function. Well, those could be supplied from a counter, from a register, from another place, and automatically you have the Hamming code, the code converted to a Hamming code, and the Hamming code be used for communication purposes. All right. This would be the end for the programming the RAM and using the RAM to implement the switching functions. It's very easy, very friendly, and it's easy to understand too. And I would like to thank you so much. Please subscribe, and I will see you very soon. Sincerely, Dr. Hassan.